Module number 11, Operators and Expressions. What is a operator and what is a expression? Operator is a symbol that tells the computer to perform mathematical or logical manipulation. Expression. Expression is a combination of variables, constants and operators as specified for the language. Generally, operators are used in programs to manipulate data and variables. C supports various types of operators. They are arithmetical operators, relationship operators, logical operators, increment-decrement operators, assignment operators, bitwise operators, and conditional operators. In earlier module, we have discussed about arithmetical operators, logical operators, relationship operators, increment-decrement operators, and assignment operators. In this module, we are going to discuss about bitwise operators and conditional operators. Bitwise operators. As a programmer, most of the times you think the data in byte, integer, long, or combination of these things. In some situations, you might think the data in bit level. The situations like data compression, data encryption, and data masking. In these situations, you have to think the data in bit level. Then the time you have to use bitwise operators. C supports 6 types of bitwise operators. C supports 6 types of bitwise operators. They are left shift operator, right shift operator, bitwise end operator, bitwise OR operator, exclusive OR operator, and ones complement operator. We have to discuss each of them one by one. Left shift operator denoted with 2 less than symbols. Right shift operator denoted with 2 greater than symbols. Left shift operator simply shift the bits towards left in specified number A. Like similarly, this right shift operator shift the bits towards right. Let us consider A less than B. Whenever this type of statement exists in your program, it simply shift B number of bits towards left in number A. That is, here specified number of bits are B. These many bits are shifted towards left in number A. Let us examine one example. 8 less than 2. 8 less than 2. Here specified number of bits are 2. These 2 bits are shifted towards left in number 8. The binary representation of 8 is 4 zeros, 1 000. Here we are shifting 2 bits. All bits are shifted towards left in 2 bit positions. Whenever you are performing A less than B, then the time you will lost B specified number of bits at leftmost end. That is, here we are performing 8 less than 2. The specified number of bits are 2. So we will lost 2 bits at leftmost end. That is, we will lost these 2 bits. Then the time the answer will become 0 0 1 0 0 0. Here the rightmost bit positions are vacant. These bits are padded with zeros. Whenever you are performing A less than B, B specified number of bits. Whenever you are performing A less than B, then the time you will lost B specified number of bits at leftmost bit positions, and that many bit positions are padded with zeros at rightmost bit positions. Similarly, A greater than B. Here B specified number of bits shifted towards right in number A. Let us consider one example: 7 greater than 2. The binary representation of 7 is 4 zeros 0 triple 1. Here we are performing right shift operator. The specified number of bits are 2. Whenever you are performing A greater than B, B specified number of bits we will lost at right end, and that many bits are padded at leftmost bit positions. That is, here B specified number of bits are 2. That is, these 2 bit positions we will lost, and this many bit positions are padded with zeros at leftmost end. That is, last 2 leftmost position bits are vacant. These bit positions are padded with zeros. Whenever you are performing 7 greater than 2, then the time the answer will become 1. Let's examine the program on left shift operator and right shift operator. Here 16 is assigned to A. The first statement of the program is A equals to 16. In second statement, A greater than 3 means we are performing right shift operator. In third statement, A less than 3 means we are performing left shift operator with 3 bit positions. 16 is represented with 16 can be represented with 3 zeros 1 and 4 zeros. We can represent 16 as 3 zeros 1 and 4 zeros. Here we are performing A greater than 3. The specified number of bits is 3. The specified number of bits are 3. So these many bit positions we will lost at right side. That is, we will lost these 3 bit positions, and that many bit positions are padded with zeros at leftmost end. Then the time the answer will become 3 bit positions are vacated. 3 bit positions are vacant. These bit positions are padded with zeros. The answer is 2. Whenever you are performing A greater than 3, then the time the answer will become 2. And third statement of the program, you are performing A less than 3. 16 we can represent as 3 zeros 1 and 4 zeros. Here we are performing left shift operator. So Here specified number of bits are 3. The specified number of bits we will lost at leftmost bits. Specified number of bits we will lost at left side. That is, we will lost these 3 bit positions. This many bit positions padded with zeros at rightmost side. That is 1, 4 zeros and 3 bit positions are vacant. These bit positions are padded with zeros. At final the answer will become 128. The next bitwise operator is bitwise AND and inclusive OR. Bitwise AND represented with single ampersand. Bitwise AND represented with single ampersand and inclusive OR represented with vertical bar. This inclusive OR also called as bitwise OR operator. Before going to discuss about this bitwise AND and bitwise OR, we have to recollect the things about logical operators. The logical operators are logical AND and logical OR. Logical AND represented with 2 ampersand symbols and logical OR represented with 2 vertical bars. Whenever you are using logical operators, the output will become single value, that is true or false, or 1 or 0. Whenever you are performing logical operators, then the time the output will become true or false, or otherwise 1 or 0. But in the case of bitwise operators, the output will become set of zeros and ones. Whenever you are performing bitwise operators, output will become set of ones and zeros. This bitwise AND simply performs logical AND at each bit position of this bit. Suppose you think A and B. It simply performs logical AND operation at each bit position of operands. And similarly, inclusive OR also, it will simply performs logical OR at each bit position. Let's consider one example. Seven and 8. The truth table for logical AND is this is the truth table for logical AND. Whenever both inputs are 1, the output will become 1. In all other cases, the output will become 0. The binary representation, consider this example 7 and 8. The binary representation for 7 is 4 zeros, 0 111, and the binary representation for 8 is 4 zeros, 1 000. Here we are performing bitwise AND operation. It simply performs the logical AND operation at each bit position. Logical AND of 0 and 0. is 0. Logical end of 0 and 0 is 0. And 0 and 1 is 0. Whenever we are performing 7 and 8, the output will become set of zeros, that is equals to 0. Let's take one example for inclusive OR. Let us consider one example for inclusive OR, 7 or 8. Seven can be represented as 4 zeros, 0, 111. 8 can be represented as 4 zeros, 1, 000. Here we are performing logical, here we are performing inclusive OR operation. It simply performs logical OR at each bit position. The truth table for logical OR is whenever both inputs are false or whenever both inputs are 0, the output will become 0. All other cases, the output will become 1. Otherwise, at least one of the input is 1, then the time the output will become 1. Let's come to this example, 7 or 8. Here we are performing logical OR operation. Let's come to example, 7 bitwise OR 8. Here we are performing bitwise OR operation. It simply performs logical OR at each bit position. 0 logical OR with 0, that is 0. 0 logical OR with 1, that is 1. The answer will become 15. Let's consider one program on bitwise AND and bitwise OR operator. Let's consider one program on bitwise AND and bitwise OR operator. In first statement of the program, we are assigning 0 and 0. We are assigning 0 and 0 to A. This is hexadecimal format, and we are assigning FF to B. The corresponding binary form of 00 is 00 we can represent as 4 zeros and 4 zeros. FF we can represent as 4 ones and 4 ones. In second statement of the program, we are performing 50 with 07. In second statement of the program, we are performing bitwise operation, that is 50 with 07. The corresponding representation for 50 is 0, 101 and 4 zeros. The corresponding binary representation for 07 is 4 zeros and 0, 111. Here we are performing bitwise OR operation, that is it performs logical OR at each bit position, that is 0 logical OR 0 is 0, 1 logical OR 0 is 1. Likewise, we will get 4 here we are performing bitwise OR operation. Here we are performing bitwise OR operation. It simply performs logical OR at each bit position. That is 0 logical OR 0 is 0. 1 logical OR 0 is 1. We will get 5 and 7. The answer will become 5 and 7. And fourth statement of the program, we are performing 4th statement of the program, we are performing 7-3 bitwise and with 3-7. The corresponding binary representation of 7-3 is 0-1-1-1. For 3 we can write it as 0-0-1-1. The corresponding binary representation for 3-7 is 7 we can write it as 0-1-1-1. 3 we can write it as 0-0-1-1. Here we are performing bitwise AND operation. It simply performs logical AND operation at each bit position. 0 logical AND 0 is 0. Likewise 0-0-1-1. The answer will become 3 and 3. The answer of 7-3 and 3-7 is 3-3. The next bitwise operator is exclusive OR operator. It is denoted with caret symbol. If both inputs are similar, the output will become 0. And both inputs are different, the output will become 1. Let's consider one example. Seven exclusive OR 3-7. These two numbers are represented in hexadecimal format. The corresponding binary form of hexadecimal format is 7-7 we can represent as 7 we can represent as 0-1-1. This 7 we can represent as 0-1-1. The corresponding binary representation for hexadecimal format is 0-1-1 and 0-1-1. Similarly, for 3-7, 0-0-1-1. Whenever you are performing exclusive OR, it simply performs logical exclusive OR at each bit position. That is, if both inputs are similar, output will become 0. If both inputs are different, then the time output will become 1. Here inputs are same, so output is 0. Here inputs are different, so output is 1. Here same, so 0 and 0 and 0. Here also inputs are same, so the output will become 0. Here inputs are different, so output will become 1. Inputs are same. Inputs are same, and here also inputs are same. The answer will become 4 and 0. The next bitwise operator is ones complement. It is represented with tilde operator. And here at each bit position it simply inverts the input. That is, if input is 1, the output will become 0. If input is 0, the output will become 1. It is a unary operator. Earlier we are discussed 5 operators. All the 5 operators are binary operators. Binary operators take 2 operands as a input. Binary operators are performed on 2 operands, and unary operators are performed on single input value or single operand. Here binary operators, earlier we are discussed 5 operators. They are left shift operator, right shift operator, bitwise AND operator, bitwise OR operator, and exclusive OR, bitwise exclusive OR operator. These 5 operators are binary operators. All these 5 performed on 2 operands, that is A less than B or A greater than B. Similarly, A bitwise AND B. Likewise, all these 5 are performed on 2 operators. Unary operators like ones complement, it is performed on single operand, that is negation of A. Let us consider one example for bitwise. Let us consider one example for ones complement, that is negation 3. The corresponding binary representation for 3 is 0 0 1 1 and 0 0 1 1. It simply inverts every bit, that is negation of 0 0 1 1 and 0 0 1 1 is 1 1 0 0 1 1 0 0. We can write it as 12, that is CC. Here the value is 12 and 12. 12 we can represent as C and C. 12 we can represent as C in hexadecimal format. So that is C and C. The next operator is conditional operator. It simply embeds the if statement into expression. The generic form of the next operator is conditional operator. The generic form of conditional operator is expression 1 question mark, expression 2 colon, expression 3. It is simply a ternary operator, that is colon and question mark and colon. It is a ternary operator. Earlier we are discussed binary operators and unary operators. It is a ternary operator. The equivalent code for conditional operator is if expression 1 expression it evaluates expression 2, else it evaluates expression 3. The equivalent code for conditional operator is expression if expression 1, if it is true, it jump to expression 2, else it will jump to expression 3. Let us consider one example. X equals to x greater than y. If x greater than y, then print or assign x to x, else assign y to x. Here let us assume x equals to 30 and y equals to 15. Whenever this type of statement exists in your program, it will check x. First it will check x greater than y, that is 30 greater than 15. If it is true, it will evaluate expression 2. Initially it will check expression 1. If expression 1 is true, it will jump to expression 2 and evaluates this expression 2. Otherwise it will jump to expression 3. That is, if expression 1 is false, it will jump to expression 3 and evaluates whatever statements exist at the expression 3. Here expression 1 is x greater than y and expression 2 is x. Similarly, expression 3 is y. First it will perform x greater than y, that is 30 greater than 5. It is true or false. It is 30 greater than 5. This is false. If expression 1 is false, the control will jump to expression 3. So the control will jump to y. Here the value of y is 15. So 15 is assigned to x. The result is x equals to 15.